Okay, maybe we can begin. Please, everybody, take a seat. And
Is the mic working?
everybody can hear me?
Yes.
Pardon?
The microphone seems not to work.
The microphone is not working.
I mean, it works in the sense that the people online can hear.
Somebody
Okay.
No,
Yeah, online
they hear.
It's just here.
Is here. Maybe I speak louder so everybody
We
can
hear fine from remote.
Okay, thanks, Matteo.
Okay.
Otherwise, this one is working.
Okay.
Does it work remotely also?
No, remotely it works. It was in this.
Yeah, but
room.
I want to make sure that when we speak on that one, it works also well remotely, so you can use it.
Okay.
Yes, it does. Thanks.
Thank you. I must say for privacy reasons that this section is being recorded. So everything is going to be recorded. So I'm going to tell you. Welcome everybody on behalf of the Tuples consortium on this ceremony of the award of the Beluga AI challenge. The Tuples project is a project that is financed by the European Union and was led by Aniti, and it's started in 2022. It's a project that is aiming at advancing in the realm of trustworthy AI, in particular in planning and scheduling. And it's composed by 8 members, leading universities and companies in Europe. There's Aniti, as I said. There's a Saarland University in Germany, Leuven University in Belgium, the Czech Technical University of Prague, Unibo University in Bologna, Airbus, obviously, and the Dutch sports analytic company She Sports, and the decision support system company that I represent also, Optit, an Italian company. That is also the company that developed the competition platform that was used during the Beluga Challenge. We're here today not only to celebrate the winning solution and to rightly award the people that made it, but also to celebrate competitions like this that helps to bring together business problems and academic studies so that new discoveries can be made even in a playful way sometimes. We will hear from our awardee, Bernardino Romero Paredes, that led his Hiverge team, and Daniel Gnad, who led the Linköping University team. Let me introduce the host that I'm going to speak after me, Romaric Redon, Chief Operating Officer of Aniti, that is the institution that led the consortium, and Florent Techtiel. I have to look after him because I am not going to say it well. A decision-making expert at 1XRT, who also I thank you very much. Also, let me thank you, Airbus, for having hosted us here. And for everybody who is here, please stay after the ceremony because there's going to be a cocktail, a welcoming cocktail.
Thank you, Michaela. So I will quickly introduce Aniti and then leave the floor to Florent for the Beluga Challenge. Aniti stands for Artificial and Natural Intelligence Toulouse Institute. It is somehow the federation of all AI teams working in Toulouse. And our main topic is around trustworthy artificial intelligence. We are operating on 3 domains of application, which are transport, industry of the future, which is the main topic which we've been investigating in Tuples, and also a lot of things linked to environment. So overall, it's somehow 300 team with mostly researchers and PhD on many seconded engineers, many of them coming from different industrial that we work with. So we have some research chairs. I won't go through all of them. It's quite classical, but I will point to one which is very close to the topic of today, which is the heroic share, which is about hybridizing machine learning approach with operational research approach. And you have there the names of the principal investigators of these chairs. The key message there is beyond the Tuples project that will be presented. We are doing fundamental research also hands in hands between industrial and academics of the site, and we are welcoming even more collaboration as part of this research chair. Quickly about ANITI. So we have the chairs, but we also have integrative programs. And I will highlight, we have 8 of them, but I will just highlight 2 of them for today. I mean, the DNA of ANITI is Trustworthy AI, and the first topic that we worked with some great success is certification of AI for usage of AI in critical systems. So you think about if we want to bring one day AI in an aircraft, or we make sure that we have all the guarantees to make sure that the AI will do what it should do and only what it should do, and or we can certify that. So that's the DEAL integrative program. And now we have another integrative program, which is called Industry X AI, where we look at several topics. One of these topics is trustworthy planning optimization, and that's the main topic of the Tuple project that will be introduced by Florent. Also, while the slide is loading, trying to reload it. One of the key aspects is to build collaboration beyond the perimeter of our institute. And one of the stuff that we do is we want to foster collaboration with academics, partner, with startup as well. And this is something that we did through the Beluga Challenge. This is something that we do on many of our projects to build challenges that could be a way to engage with more collaboration. So, sorry, technical issue. Okay, let's say show anyway. So here, so ANITI is promoting such challenges, and you will learn more. Of course, I mean, we are very well connected to all EU initiatives. I mean, Tuples was a Horizon project, but also we are connected with AI factories, EDIH facilities, all this stuff that we get from Europe to accelerate AI research. Last slide is just to say also these challenges, and especially you will see today, has been a way to connect to Linkoping, to connect to iVerge, to SIA. And yeah, we are looking forward to explore a potential partnership with ANITI. And here you see all the partners that we have, and we're very happy to go further. Then I leave the floor to Florent to go more deeper into the Tuples project.
Thank you very much, Romaric. Yeah, so good afternoon, everyone. I'm Florent, working in the 1XRD team, so Airbus AI research team in Central Research and Technology. So I won't take too much of your time because you obviously want to hear the winners of the challenge, for sure. But I will quickly introduce the challenge so you have a quick overview of what it consists of. So in case you are wondering how this kind of challenge looks like, it's this. So we had quite a lot of fun. The teams around the table with this big plushy beluga here. It was quite nice. Now, honestly, that was not like this, but more like this actually. Also us, as we worked on the problem on our side, because we figured out that the problem was quite difficult to solve, quite challenging, and we sometimes work alone in the dark, trying to break the puzzle. So this is why we decided in the project to organize this challenge, and we chose actually the Beluga use case because it was a nice planning problem, which was also quite combinatorial. And so Michela actually did a lot of announcements. So on the Tuples website, also on social medias like LinkedIn, but also in a number of summer conferences. So I think I will be quick on that one because you already had quite a lot of Tuples. So Horizon Europe project between academics and industrial partners. So including Airbus, which is presenting this use case today and coordinated by Anity. So this Tuples project is really about trustworthiness in planning and scheduling. So you might know, I think that planning and scheduling is actually a key technology for autonomous systems when you have to take decisions over time. So choosing the right actions and when to do them. With some objectives can be a goal to achieve, some binary goal, or minimizing a cost, and taking also constraints into account. Like for instance, time constraints when you know that you have to begin to do an assembly task, for instance, you can see here at a given point in time. And the decisions in most of real industrial use cases must be trusted by the operators if we want them to be accepted in the business. It means safe decisions, robust decisions under various uncertain events, for instance, disruptions on the manufacturing line. That must be scalable, meaning solving the real problems, being able to tackle the size, but also their complexity. And finally, to be explainable. Historically, if you look at the different approaches that have been investigated in research, usually they are split in two main classes. So like reasoning or model-based methods, where you start from a description of the problem in mathematical form and can be logical form, can be mathematical constraints, equations. And from this mathematical model, you will run some reasoning algorithms like search algorithms, constraint programming algorithms, mathematical programming like MIPS, for instance, and it will produce a plan which is usually a solution that you can translate to a plan which is usually interpretable. On the other side of the spectrum, you have learning or data-driven methods which don't start from a mathematical description of the problem, but rather from data. And actually, they learn from data, from examples, from simulations of the system, expert rewards also, to produce a policy which is quite an opaque, let's say, representation, can be a big neural network nowadays, from that you can then execute to produce the next action to execute in your plan. And if you look at the pros and cons of each approaches, usually it's well admitted, let's say, that reasoning methods are safe, stable, quite explainable because they are interpretable, but not adaptable and scalable. And actually, this is the opposite for the learning methods. This is why in the project, we investigated the hybridization of learning-based methods and model-based methods. So this is the first pillar of the project. The second pillar is to provide guarantees, okay, typically safety guarantees on the policies that can be produced, for instance, by reinforcement learning algorithms, just to take an example. And last pillar, explanations, very important one. So we want the algorithms to be able to explain to the end users why this action and not another one, for instance, was taken. And we demonstrated those technologies in a number of demonstrators that I won't detail here. Among them, the Airbus manufacturing ones, which are actually the topic of the challenge. And finally, we also, during this project, capitalize the technology in a number of libraries, the Tuples Lab, Scikit-Decide library, and the self-evaluation tool, which is a tool where typically a user would check a number of properties, can be also ethical concerns, to be sure that the decision-making tool that they will release is okay. Okay, so for the challenge, in Tuples, we looked at two manufacturing problems, the Beluga one, which is the challenge, and task allocation and scheduling, which is another use case, which consists, in fact, in allocating teams of people to transportation tasks. And one of those transportation tasks actually are the Beluga ground logistic actions. And all of this is part of the heavy handling control system, which is used especially in Hamburg, but not only in Hamburg, also in other sites like Toulouse. If you look at this problem, the Beluga one, this is a satellite image where you can, from Finkenwerder in Hamburg, people remotely should use my mouse. So here, this is the Beluga hangar where the Beluga arrives, and here you have temporary storage racks where the parts which arrive in the Beluga or from the production line have to be stored temporarily in there. I will detail it a bit more detail just after. In fact, you have to plan how and where to store those parts into the temporary racks, in fact, using shared resources like trailers, for instance, and also some hangars that we don't see here, equipped with cranes. Taking also uncertainties about production demands and Beluga flights that can be impacted by uncertain weather, for instance. It's actually a complex and combinatorial problem, which is done manually today by teams of humans, which tend to use rack buffers to absorb uncertainty, because that can be actually complex to solve by hand. And they don't want to be blocked, because if you block the system, you block the production of the aircraft in the plant. So what we propose is an automated plan generation technology, which can also anticipate uncertainty, and actually Hyvert will speak about it. You hear the noise, no? Okay, so some words about the problems that we proposed for the challenge. So you see on the left here, the Beluga arriving with some parts on a jig. So the part, for instance, here is a wing, which is on top of a jig, and the jig itself on the trailer. Okay, so you have the three things: the part, the jig, which handles the part, and the trailer. And the parts arrive in a given order from the Beluga flights, and you have to store them in this rack system before then sending them to the production line. And the tricky part is that you must send the part in a given order to the production line, which can be different from the arrival order in the Beluga. This is why you have to manage here, like so some games, like you have to take a part and swap it to another rack in order to be sure that the ordering arrival of the part here will be transformed in the right ordering delivery to the production line. And the parts can only slide on one way or another. So for instance, if you want to send this orange part to the production line, you first have to freeze the path for that guy by swapping this blue part, putting in the rack before sliding the orange part and sending them to the production line. So if you think about this problem, imagine you have a lot of racks, a lot of parts. It can quickly become a nightmare and a quite important puzzle to solve. In the competition, we propose to solve problems for one flight up to hundreds of flights representing months of operations, right? With lots of racks and so on, which is totally impossible to handle by hand, in fact, and also long term. And so this is why we wanted to propose this challenge, to get ideas and solutions from the external world, to allow best-in-class AI scientists, so researchers, startups, and we have representatives of the two worlds today here, play and have fun, I hope, on our real-world industrial problems. And it was also an opportunity to develop a platform for AI decision-making challenges, because you can find a lot of platform for AI challenges, but not really for decision-making challenges, which is a bit different from image recognition or language processing tasks. So people could register in July 2024 until November. Then we launched the platform in November 2024. There was kind of a nurturing period for 2-3 months. And then the competitors could submit actually their solutions. They could submit successive solutions for approximately 2.5 months. And then we evaluated everything during one month in April. And we are here today to deliver the diplomas, let's say, to the winners. So as I said, we developed this competition platform, actually developed by Optit and owned by them today, but they kindly proposed us to maybe reuse it for further AI decision-making challenges at competitive prices, so by the Tuples partners, but also including Airbus, should we want to propose other decision-making challenges in the coming years. And it's really, I already said it, a one-of-a-kind platform. We believe that you would not find other platform for decision-making, which is important here challenge. There were 2 tracks and 3 challenges. First track on scalability, both on with deterministic probability settings. So 2 challenges for the first one, and a second track on explainability. I will go fast on this. And today, so we are pleased to announce the winners for those two challenges, actually, and two tracks. So first winners for the deterministic and probabilistic track, because they provided a very good solution for both tracks. So Hiverge, and we will see them in a minute on stage. Then for the explainability track, it was Linköping University. They will also give a talk today, just after. And we also had a special prize for the runner-up competitors with SIA partners, which are not here today, but we came second on the scalability track. And so before giving the floor to Romaric again and the winners, I would like to thank a lot and congrats the Tuples team for having organizing the challenge, because I can tell you that it's a lot of work. Actually, the first picture which you see before coding in the dark maybe was also to code actually the competition platform and all the scripts that the competitors could use. So a lot of applause for them also, and congrats. And Romaric.
Yeah. So I think it's the time now for providing you with the ceremony I'll call you on stage. So do we go first with Hiverge, I suggest? Yeah. No. Yeah.
No, that's nothing.
That's everything is in there now?
Yes.
Okay, sorry for. So we're very pleased to get you on stage.
Okay.
So you will see you have some small models of the Beluga. Okay.
Thank you.
On the official, if you want to get a nice picture of you with some of that. I can handle some of these for you. Thank you. I can get them like this. Thank you. Thanks a lot. Yeah, thank you very much for having found the challenge, having spent time on it. Yeah, we are very looking forward to explore even further what can be done with your solutions.
Absolutely. No, thank you. And thank you for organizing this amazing challenge. It was a lot of fun. Definitely, I know that there was a lot of work behind, I can tell. So yeah, thanks a lot for organizing it and for also organizing this day today. The visit was great, was amazing. So yeah, I enjoyed it a lot. Thank you.
So then we will go with the second prize on explainability with Linköping University. And Daniel, yes, on the come here. So who wants the small Beluga? Do you want them or? Let's do it like this. You want one of them? Yes. Thank you really for your, I already said it, I think the explainability aspect is really something that can unlock a lot in terms of creation of value, because for long, I mean, operational research on combination with machine learning is providing interesting solutions, but as long as you cannot explain, it's really something that is slowing the adoption. So thank you very much for your contribution on this path to get more explainable results. Ah, yeah, no, so we can take the picture with both of you. Yeah, go ahead.
Thank you very much. Thank you very much.
Okay. So now we will go through some presentation of what was achieved by on the first topic, which was the scalability challenge, and we will see what Hiverge did. Do you want to use that one?
Okay.
It's up to you.
So I guess listen from here. As in, or I can even. Wait. Well, yeah, just figure out what's the best. So, okay. So, okay, so there we go. Yeah. Thank you. So yeah, so I'm Bernardino. I'm CTO of Hiverge and co-founder, and I would like to start this presentation by telling a bit about our story, about how we started this company, and also how we ended up participating in this challenge, in the Beluga challenge. So let me go back to 2019. So in that year, I was a Google DeepMind. I was working on protein folding, on the AlphaFold project that last year won the Nobel Prize. And one day, one afternoon, by the end of that year, Hussein Fawzi, a colleague of mine that wasn't working or was working on a different project, he came to me and then he started talking about ideas about leveraging AI for discovering new algorithms. And he had all sorts of ideas. I also had some ideas, and we were discussing a lot. And to be honest, that afternoon, I felt like there was a lot of potential there. I found that his ideas were quite revolutionary, and I really wanted to start working on that. So soon after, we started a team within DeepMind Science. That was the computer science team. And the whole point of that team was to do that, to leverage AI for algorithms discovery. And I found that really interesting, at least at two levels. So first, from the point of view of the technology, it was fun, a fun thing to work in. But also, it involved coming up with new algorithms, right? So the purpose, the goal was to discover new algorithms for important tasks, for important use cases. And as we all know, algorithms run the world. So the second point I want to make here is that this has a big impact. So our first project was Alpha Tensor. And in that project, what we aimed was to discover new and better algorithms for multiplying matrices. So matrix multiplication is the extremely common task, extremely common operation within many algorithms everywhere. It's the workhorse of many algorithms. Like, well, neural networks at the end of the day are a sequence of matrix multiplications with nonlinearities, and also many other tasks such as weather forecasting and so on. So even improving a bit matrix multiplication can lead to a lot of gains. So that's what we did. We use reinforcement learning in order to tackle that, in order to let the model learn and improve or discover new algorithms. And after quite a bit of effort, we managed to have a system that was indeed able to find new algorithms that were better than the state of the art. It was actually quite a success. It was the first time that AI was leveraged to find new algorithms that were better than the state of the art. And as a result of that, we got a paper in Nature, and it was quite an interesting project. However, it was also quite painful, to be honest with you. So you see here, it took us quite a long time to get the results out. And the reason is that reinforcement learning is quite, and we were using actually AlphaZero, which is a specific system, quite complex system of reinforcement learning, is quite a beast. So, and it has several problems. So for one, it has to learn from scratch. The training process is quite long and expensive. Also, it's at the end of the day, what you get is a neural network that is essentially a black box, so you cannot see what's inside. And also, the code base is really long. I mean, it's really complex. It's I can assure you. So we were working with one of the best teams on reinforcement learning, and even with them, it took us quite a while to make this work. So by the time we finished, and that was 2022. So back then, LLMs were starting to show, to show their potential. Back then, ChatGPT wasn't still there, but it would appear at the end of that year. But even then, even before that, it was pretty clear that they had a lot of potential. And in particular for us, what we wanted to use them for was to deal with code, to ask them to produce code. And the good thing about working with code is that we can automatically evaluate it, right? So you get a piece of code and you can run it, and you can automatically tell whether the code is running or not, and even how good the solution of that code is, and so on. And that's an important thing, because unlike natural language, in natural language, you need a human in the loop, right? You need a human to say, okay, this output of this LLM is actually good or not. But with the code, you don't need that. You only need an evaluator that automatically assesses the piece of code that comes out of an LLM. So coupling an evaluator and an LLM ended up being a pretty powerful idea. It's a very simple idea, but it's very powerful. And that's the initial point, that's the starting point of our next project, that was FunSearch. That's essentially what it did is to take this idea and do it properly. And yeah, essentially creating this conversation between LLMs and evaluators or simulators. And in this way, yeah, we create this ever-improving loop where you get better and better pieces of code, better and better versions of your code. So we did that, and we applied that to computer science problems and to theoretical math problems as well. That was the point of doing this project. And we succeeded at that. We found new results that were actually pretty interesting. And also we published a paper in Nature again. But then we realized that the scope of applicability of FunSearch was way broader than that, right? So it can be applied to many other tasks, many other real use cases. In fact, we started at Google. We applied that to find a job scheduler that takes jobs to servers, and it did so in a way that it improved the ones that they were using back then. And in doing so, Google was able to save a significant amount of energy and cost. But then Hussein and I saw a lot of potential, and we decided to go out of DeepMind and to start a new company together with Hamza, who is a professor at the University of Cambridge. And we did that particularly for two main reasons. So one is because we thought that was the best way to accelerate this process of building these kind of systems, to accelerate the process of making them being as good as possible. And we had a lot of ideas, and we still have a lot of ideas to do that. And the second reason is to allow anyone to use this kind of systems, to work on real use cases, around the world. Okay, so our technology, the Hive, we call it the Hive. So you can see this as a code optimization agent that autonomously finds the most effective algorithms for a given task that the user provides as an input. And you'll see that soon in the demo. So what we are after here is that we want to enable enable teams to do to go beyond what they have been able to do. The kind of problems, the kind of tasks that I'm talking about are not just things like implementing a web app, but what we're after here is about algorithms that are at the core of the business of a company, right? So you are really algorithms that really require whole teams of experts to work hard in order to find an algorithm that really meets the requirements of the task. So what we want to do here is to enable those teams to evolve those algorithms, which can be done in a matter of days instead of weeks or months or even years, and allow them to think about tackling even higher, even more complex problems of a higher caliber. And here, for example, now I'm thinking about Airbus. So I believe there are many such problems in which we can have a big impact. Problems that involved planning, scheduling, decision-making, problems such as satellite constellation planning, involving planning orbits of satellites. At the end of the day, is about deciding which satellite will cover which part of the region at a given time, and even taking into consideration things like uncertain things such as clouds that might appear here and there. So the Hive is pretty good at dealing with uncertainty. Also, airline optimization, electronic chip design. I believe there are many combinatorial problems there, combinatorial optimization problems there. Flight scheduling and so on. But of course, today here we are. The reason for why we are here is to talk about the Beluga challenge. And so I'm gonna talk a bit about that now. So as Florian was talking about before, the challenge was is about it's a logistic planning problem. It involves storing and managing different components transported by Beluga aircrafts. And by the way, I found this competition thanks to Matteo Pozzi, who I see he's with us. And by the time the competition appeared, I remember we had a first version of the Hive already implemented. And then when we saw the actual competition, the actual challenge appeared online, all the details, I remember looking at it and thinking, well, this is actually a pretty good use case for us. I mean, it has everything we want from a problem to apply the Hive on. So that's what we did. To be honest with you, I had no idea, neither I or anyone in my team, we had no idea about planning. We didn't do any planning before. We had no idea about what a PDDL was. But we learned about that by going through the documentation. We learned a lot. That was actually pretty nice. And then what we did was to have an approach, or to start working on an approach that combined two things. So it combined a search algorithm that we had implemented ourselves with a heuristic that was evolved by the Hive. And we submitted that, and we got the best results on both deterministic and probabilistic. The probabilistic part only involved a few changes. We can easily accommodate for that in this case, also because we thought about that beforehand. But the point is, back then, we had to think quite a bit about how to deal with, how to leverage the Hive. But then after the challenge finished, we decided also to look at how to apply the Hive to solve the problem from scratch, to see how well it does. So I'm going to show you a demo. Let me see here. Okay, so first of all, this is the front end for now of our system. And as you can see here, the input is just a repository. So a repository has a bunch of code organizing files and directories. And here this is a repository that we created ourselves, starting from the code provided by the challenge, by the organization. The code of the challenge is here, so this is everything's here. We make use of that, and then here we put the data, as in a lot of the instances for convenience is there. And then other key things are, well, the README. Here we have a README. This README is important, or it's interesting, or it's useful, because it allows the LLMs to get some context about the problem, right? So it allows them to know what this problem is about, and hopefully help them in coming up with good solutions. Now another file is this one. This is the file that we want to evolve. Now, in this case, we're starting with quite a lengthy file. And what we do here, what we want to evolve, is this file that what it does is, at the end of the day, it takes as an input a problem, a Beluga instance. And what it does is to produce as an output a sequence of states, a sequence of actions. So it produces a plan directly. So this is not search, but it directly produces a plan. Okay, and finally, about this, we have the evaluator. That's the key part. So we have to define a piece of code that assesses how good the rest of the repository is, in particular the part that we're evolving, right? So in this case, we just have this function that goes through all the instances or some of the instances of the data directory, and then it scores them. It provides feedback, and particularly so it provides fitness in particular, which it's what allows the system to know which version of the code is better than another. And by the way, here in this case, well, we use some fitness based on first of all, we favor problems being solved, of course, and then among the problems that are solved, we of course prefer the ones that are shorter. So the fitness is a measure of that. Okay, so that's it. So we can now take the repository here and put this inside here. We load it, we select a branch, which will be main in this case. And then now we select the code or the pieces of code that we want to evolve. So as I was saying before, what we want to evolve is policy planner. So here we can select parts of this file. For example, we can select functions here, or we can even select parts of code. But in this case, we're going to submit everything. We want to evolve everything. So we submit, and finally we put the evaluation command, which is evaluator. So we run the evaluator like that. Yeah. So yeah, that's the way we have to know how good a version of the code is. So now we can click on run, and what this is doing is just to use the current version of the code and to run the evaluator on that. That's the only thing it's doing at the moment. It's not running the Hive, not yet. So it's just to have the results of the current versions. And here you can see for each problem in the validation set, we see whether it was solved or not. So sometimes we see failed, as in it wasn't able to find a proper plan to solve all the required constraints in the instance, and so on. So here we see that the total solved instances in this case was 33 out of 70. And yeah, so that's the starting point. So now we can click on launch. And now, in fact, we are starting running the Hive under the hood. We can now click in here. Nothing will appear because it's still too soon. But yeah, now an experiment is running under the hood. It will take from 5 to 10 minutes, usually. So in the meantime, I can show another experiment that we ran before. So here again we start from the piece of code that I mentioned before, and then we can look at the end of the code. So first of all, let me tell you that in this plot, the x-axis is the time in seconds. So in this case, we run an experiment for about 4 hours. And then the y-axis is, of course, the fitness. So of course, the higher the better. Okay, so now we can look at the last piece of code that was found. So here we can see the differences with respect to the initial point, with respect to the starting point. And then we see that there are many differences. The code, the Hive is able to provide a lot of modifications here and there. We see, for example, that it's able to create new functions here. So this is a completely new function. That's all sorts of things. But interestingly, one thing that it produces, the LLMs produce, is comments everywhere or quite often. And these comments are not rubbish, but they are actually meaningful. You can understand the code better if you read them. So that's also a nice thing to see. And now if we look at the results, so then so you can see that now this version is able to solve 69 out of 70 of the problems in the validation set. Great, but when I started the demo, I was saying that we also were trying to start the Hive, starting from scratch, starting from essentially from nothing, and that's what I want to show you here. So in this case, we have this piece of code here. This is our starting point. These are only 7 lines of code. It's essentially boilerplate code, just a header of a function, and that returns the initial state. So essentially, it does nothing. And of course, if we look at the results, it doesn't solve any problem, as you can imagine. And what we do is just to run the Hive on top, starting from that point. So so we did that. We did that over the span of 2 days, which is exactly this amount of seconds. And then if we go here, we end up at this point in which we can see the difference, of course. So we start from nothing, and then we ended up having let me see if I can. We ended up having quite a complex piece of code. We don't have classes here that came out of nowhere, and a lot of methods and functions here and there. And it ended up being around 1,600 lines of code. But the point of this is not how long it is, but rather how effective it is, right? How good it is in solving our problem. And about that, we can look at the results here. So we see that it's able to solve all of them, actually. So it's able to solve all the 270 problems that we were using in the validation set in this experiment. And just let me emphasize that it did all autonomously, right? So it started from here all the way up to here without any intervention in the meantime on our side. Okay, so let me go back to the presentation, and I'm actually going to continue a bit on that plot. So this is the same plot that you saw before. Just put it in a different way. Now we have hours here in the x-axis, which I think is a bit easier to get. But then the interesting thing that we have added here is different points. So essentially, Kerry from our company, once the experiment was done, he started looking at how the Hive did what it did, and he found some interesting breakthroughs in a way that the Hive was getting over time, over the course of these 2 days. So first of all, for example, we can see here, it quickly is able to produce a really direct, very simple strategy that was able to solve more than, one problem or more. Non-zero, exactly. Non-zero, more than, non-zero number of problems. And then after that, it quickly went and found more sophisticated kind of strategies, like identifying blogging geeks and handling them somehow. Further down the line, is able to detect and handle deadlocks, and also to predict how an action would have an impact in the future with respect to both the list of jigs expected in the production lines, and also the ones coming from the Beluga flights. All interesting things like producing classes to restructure the code, which I found quite amazing. So as you can see, and also I guess I wanted also to convey that when I was showing the code that I was showing is not spaghetti code, right? It's actually quite interpretable code. It's very well organized. If you have classes and so on. It's kind of easy to follow. And then yes, it discovered all sorts of things. By the end of it, by the way, it was even using meta heuristics to refine the plans that were found. So to be honest, when we saw some of the ideas that it came up with, we were actually pretty surprised and quite positively so. Right. So of course, Beluga is not the only planning problem out there. So after we started looking into what PDDL was, we realized that there were also other competitions out there. And in particular, there was this competition, IPC in 2023, which proposed several domains, 10 domains, different ones, like, for example, Sokoban was one of them, and a few others. And of course, this competition is over. I mean, it's 2 years ago. But what we could do is to apply the Hive and see what happens and see how well it does. And what we did was to essentially provide as context, as an input, we provided a brief description of the problem and then the PDDL domain. And that's it. And then these are the results. So we compare it with a search with a blind heuristic, like a non-informative heuristic, and a power-lifted method in gray. And we can see that the Hive gets the best results, significantly better results than the others, and particularly so for the hard instances. There you can see that it's a huge difference. Okay, so now I want to go back a bit again about what the Hive is. So as I was saying before, the underlying idea, the starting point of all this is about connecting an LLM and an evaluator, or a simulator, if you want. So by connecting these two pieces together, so essentially you get that the simulator provides feedback and provides also with information about which are the best found algorithms so far by an LLM, and so in that way we can leverage that to ask the LLM more about this kind of algorithms, right? So this simple idea can be taken very far, and can be enlarged by using different ideas. The main one, or the starting one that we've been doing since the beginning, is to scale this paradigm by using a number of LLMs in parallel, but also a lot of simulators, a lot of evaluators in parallel. And that allows us to really evolve a population of code in a quite broad and fast way. In that way, we can store the space of different algorithmic solutions in a very efficient way. But of course, we have been incorporating other ideas from different fields. Like, we have some ideas from formal symbolic methods. We have search. We also bring some ideas from agentic systems, and also from reinforcement learning. So before I was criticizing a bit reinforcement learning, but it is true that there are some ideas that we are also borrowing. So that's those are the strengths of the Hive. Our strengths as a team are also that we've been working on these kind of systems for over 3 years. So we get a pretty good know-how both at the research level, but also at the engineering level. I want to once again emphasize the set of advantages that it has to have a piece of code as an output, right? So before, Florence had a very, very nice slide about neural networks below, and I think it was reasoning models on top, and how you had 5 kind of properties like interpretability, adaptability, and some others, and none of those 2 approaches were able to fit all of them. Actually, yeah, it was like half and half essentially. And I really believe that this approach, I mean, this kind of system, which code as an output, gets the best of both worlds. And actually, it ticks all the 5 boxes. In particular, where it provides an algorithm, it's definitely fast. Usually, code tends to be fast, and it doesn't need, for example, doesn't need specialized hardware like neural networks to run on. Of course, it can be adapted like neural networks, but unlike neural networks, it is explainable. So neural networks is essentially a black box. You only see the inputs and the outputs. But here you can look at the code. You can try to understand the code, and you can even tinker with the code. You can modify the code if you want. You can do whatever you want with that. And also, it is safe and it's easy to deploy. Okay, so just to finish the presentation today. So yeah, just first of all, one thing that happened today also for us is that this morning we came out of stealth, so we're launching publicly, and it's been quite an interesting day because of these 2 events happening together. And in doing so, we have one of the things we've done today is to release a blog post in which we talked about applications of the Hive. And one was planning in the context of Beluga, but also we talk about a different kind of application, which is about making the training process of language models and other neural networks more efficient. And essentially, it's using AI to improve AI. So if you want to know more about that, please feel free to visit our blog post. It's all there. Also, we can talk about that later. But just to finish, I would like to go back to our value proposition and to emphasize that the Hive provides value by coming up with solutions for planning, scheduling, and decision-making problems. And I believe that you have many of those here, right? So you've seen what the Hive can do for the Beluga problem. So imagine what it can do for all the problems that planning and scheduling problems that you have here. So here, we as Hive, we would love to explore that with you. So thank you, and I'll be happy to answer questions.
Okay, thanks a lot, Bernardino, for this great talk, which raises a lot of very intriguing questions.
This is the experiment we started.
Okay, already, all right.
So you can see.
It's percentage, 95% of.
Yeah, I mean,
well, okay.
Yeah. Anyway, yeah.
Okay, and by the end of the Q&A, it will be already at 99, maybe. We'll see. So, any questions?
I have plenty of questions.
Okay, Sylvie.
I'm dealing with them, right? So.
But go on. Ask your first question now.
Oh, I don't know. So, I mean, okay, one question. So, fundamentally, what makes this so successful in comparison to, let's say,
reinforcement learning, where in reinforcement learning you would explore, you would get a reward at the end in this case, which is what you're getting at the end, every time you do this evaluation. So at the end of your planning episode, you get these rewards once you've reached the goal. Is that the fact that the LLM is operating in this structured space of programs where, I don't know, do you think it's got some strategies to actually evolve programs on its own, and how does the rewards enact these strategies? I mean, to me, it's a mystery. But by the way, I'm blown away, right, by the fact that you can start from nothing and solve 100% of the competition problems. So congratulations.
Thank you. Well, you mentioned a lot of questions. Yeah, thank you. It's CV is great. So, okay, let me start with why it works so much better than reinforcement learning. So one, well, I guess there are several reasons. One of them is that with LLMs we don't start from scratch. LLMs have seen everything out there, so they have already a lot of information. So that's one thing. But another thing is searching the space of code. I think is particularly powerful. At the end, like particularly in the cases where we start from nothing, it grows the code in a way that it tries to, in a way, find the simplest piece of code that does something. And I mean, I don't want to get into a lot of complexity and things like that, but because these are, of course, are hypotheses. But I believe that there is some element of code enabling search in a way that allows to get to more complex kind of problems. Also, by virtue of, again, going back to the fact that LLMs have seen a lot of code and have, well, they know about all the kind of abstractions and all that. But that's one thing about, also related to another point that you mentioned about how the fitness is used. Yeah, it's, at the end of the day, what we're doing is evolution. So the fitness is used to decide which elements of the which individuals let's say in the population of version of the code that we have will be part of what we send again back to the LLMs. And that's the main area. That's the underlying mechanism. We have some other more complex mechanisms, but that's essentially it. That's really the core of it. So that ends up working really well. I mean, to be honest, I don't really have a proper answer. I mean, we started this back in the days of FunSearch. We started this really as kids that play with LLMs and put stuff together, and then we realized that, oh, that actually works. That actually works pretty well. And we don't really know exactly all the reasons under that, like theoretical reasons about why it does work, to be honest. But it works pretty well.
Yeah. Thank you very much. Very, very impressive work. Join CV in that comment. So one question, bit more technical. While you're working on the Hive, I guess there were multiple new iterations of LLMs coming out, right? Do you see any major difference in, for example, convergence speed or the quality of the final solution if you let it run for a certain amount of time when using different kind of different ages of LLMs, say? Yeah.
Right. Yeah. So I guess just to make sure I understand. So you mean when using different models, different LLMs, how that affects the final?
I'm more thinking about if you go from ChatGPT 3.5 to the most recent model.
Sure. Yeah. I mean, it definitely has an effect, and we keep updating. Essentially, when we do these experiments, we have an ensemble of different models. We keep updating that as new models appear. And yeah, definitely has an effect. So, okay, first of all, there is a trade-off here. So we want and particularly for experiments like this, where the evaluation here is very cheap to compute. I mean, in this case, it's quite fast to get to run the evaluator and get the feedback. In this kind of cases, you really have a trade-off between efficiency of inference in the LLM and how powerful it is, right? So if you employ the biggest models out there, you will get very good pieces of code in general, but you will also have to pay the price of waiting for them to get out, and also the actual price of the money. So there is this trade-off there. But in general, it is true that as better models appear, and as we combine different kinds of models in this kind of spectrum, results ends up being better. Like for example, the example I showed before, where we started from nothing and got this solution. I could be super surprised if we were able to get something like that about half a year ago, let's say.
Are there any question online, maybe remotely?
Someone wrote down.
Someone wrote a question. Oh, okay. Check. Just checking the message. Okay, so I'm reading it. I am also space engineer, and how can I involve in such challenges? How to follow it? As you mentioned that you were involved in it. I am completing my master thesis in 2 months. Okay, that's more questions for us. Okay, I will answer by email, I think, because we're running out of time, but you get an answer. Giant? Okay, short one, a very short one.
Yeah.
Yeah, it is not. It just happens that they end up being useful, and they end up being producing pieces of code that get better fitness, even in this, also in the long term. But yeah, essentially that's the answer. Like solutions that contain classes for a specific problem, those classes ended up producing better solutions, better pieces of code, better versions of the code that there was that don't.
Do you need to simplify a bit the final code to remove maybe some things that were obsolete, not used anymore?
Right. I've seen that happening in the past. I don't see that happening that recently, by the way. But I myself, I haven't looked much at this code, by the way. It's been mostly Kerry, the one that's been really digging into that. But in general, whenever a function or whenever a class appears there, it's because it's being used somewhere else. In general, that's usually the case. Still, sometimes it might be the case that it may happen that it goes into doing something that doesn't get used, but that's rare.
Thanks.
Thank you. So we need to switch to the talk of the explainability challenge winners. Thank you again very much.
Thank you. Thank you.
And let's continue the discussion at the cocktail. So, okay. Share window. Where is it? Okay. And view, I guess.
See you soon. Okay. All right. Thank you very much. I'd like to very much join Bernardino in saying big thank you to the organizers of the competition. I know that it must have been a lot of work to set this up, and also very big thanks to the very patient supporters that kept answering all of our technical questions. Very much appreciated. So yeah, I'm Daniel. I'm bringing with me Elliot, who's a PhD student in Linköping University. And besides thanking you guys for organizing, I'd also like to thank our team at Linköping University. So what we actually did, that might be interesting for some of you, is that we were running a PhD level course around the Beluga competition, where during the course we developed several approaches. We also competed with Bernardino and his team on the scalability track. Didn't quite match their performance, but yeah, I'd like to basically join Florent in saying it was a lot of fun. I mean, we really enjoyed it a lot. It was a very unusual PhD course, a very unusual experience for us as researchers, mostly working on theoretical aspects usually, like developing new algorithms, and now being able to tackle a application that is very close to something that is being actually kind of solved here at Airbus very regularly. That was a lot of fun for all of us. So for the technical part, I'd like to hand over to Elliot, who was taking the lead in the explainability submission. Yeah, enjoy that.
Thank you very much. And hello, everybody. So as said, are you hearing me all right, by the way? Okay, perfect. I'm here to talk to you about our solution for the explainability challenge. And we've all heard Hybert's talk just now about how you can solve problems, right? And I think we all share the same vision for how these systems are going to be used in the future. They're not just going to be used by themselves, and they're just not going to replace us humans. Instead, we're going to work together and do more together than we could do by ourselves. But when you step into this realm, there's a lot of questions that crop up. Questions like, why in the world would the system tell me to do this, right? And answering these sort of questions is fundamental for getting understanding, which is fundamental for getting cooperation, which is fundamental for moving towards this future together. These were sort of questions that drove us towards looking at explainability track this year. And explainability, before I get into it, is really, really broad, right? It can be anything from looking at neural network weights to pushing over robots and seeing if they get back up. So for that reason, I'm not getting into most of it. I'm not getting into really any of it. I'm just getting into our solution today. And what we did at a really high level is a thing called counterfactual contrasted explanations, which means that we explain the solution we got by comparing it to a solution we could have gotten under other circumstances. But I'll get back to what that means in a bit. Before we get to that point, though, I think it's interesting to look at what sort of thing it is we want to explain in the first place. Of course, that is some variety of AI system, an intelligent computer program that gives us some outputs. Perhaps it's chess moves or it's Beluga plans. And there's a bunch of these different systems out there. We've heard a few of them now, right? But the most famous perhaps is like neural network-based solutions. But while they're famous, they're also equally infamous, right? For being hard to understand. We've heard about this repeatedly, and figuring it out is like looking at spaghetti code, not nearly as nice as Hybert's stuff. And it's all just random numbers. For that reason, the understanding of these systems is years behind the actual power and implementation of them. On the other side of this divide, we have the classical solvers. Stuff like planners, in our case, or SAT solvers, CP solvers, all of that. These systems instead are designed by humans from the ground up, and we really understand them in depth. But still, if you just give a problem to them and they solve it, the reason for why they gave you this particular solution is oftentimes just that it satisfied all the logical constraints. And probably that's not what you want as a human when you ask the system that question. But what both of these types of systems have in common, as well as most other systems, is that they operate over models and over inputs. Perhaps there is a Beluga model like the one we had here, which we pass to the solver, which then solves it. or there's a chess simulator around it, or there's some other variety of inputs which control what the system does. And what we do is we take the task, we pass it through, and then we change this input. And we change the input in such a way that by resolving this new input, we get a new solution, and we can compare the two. And the beautiful thing about this is that we really don't need to look at what the system does inside. We can treat it as a black box. And in that way, you can apply this for neural networks, classical planners, or anything in between. Be that for Beluga planning, or for satellites positioning, or whatever else it is you're doing. But let's take one step and become a bit grounded and how we can do this. Because I think saying you can do it to anything is kind of vague, right? So for Beluga, for the explainability track, there were a lot of questions. One of the questions we could have to answer was, why is jig X loaded on rack A instead of another rack? And for each question like this, we manually devised a reformulation, a way of taking the original problem and changing it to answer this question. For this one, that reformulation involved forbidding placing X in A and enforcing that it had to be placed in B. So if we make this change to the initial program, we'll see what the best we can do is, if we do like the person that asked the question suggests. This could come with a lot of differences, right? It could be that plans get a lot longer. It could be that they get less robust, or it could do nothing. It could be that choosing A over B really was just an arbitrary choice. But by making these reformulations, we can see what the answer is. And by comparing the two in a second, we can get good answers. These are all the questions from the Beluga explainability track. I won't go through all of them for the sake of time, but I'll give you at least a little bit of a second to read them yourselves. All right, so I think that's all the time I have for leaving you guys to read for yourselves. But I want to push again for that. While this is what we did for the Beluga, you could also do other reformulations, other approaches, other tasks, whatever it is you need to be working on. But now that we have these counterfactual options here, we get new plans and the old ones. And now we just need to compare them, right? And figure out what the difference is. However, that can be a lot of work. It can be really complex, and the plans can be several hundred actions long. So getting any clean outcomes from that can be tricky. At least it can be tricky for a human, right? So similarly to Harvard, we employ an LLM for this. And the prompt here is, of course, adapted by us. It follows standard prompting techniques. We tell it it's an expert. We explain the target audience, the scoring criteria for plans, as well as giving a one-shot example how to explain something. And we take this, we pass it off to a closed or open source LLM, depending on your security needs. And out comes a high quality explanation, which is ready to be given to a human. And this finalizes the system we decide. So to look at this all together, right? We start by getting a task. We pass it through our solver and we get a solution. But the human has some form of question about this solution. So depending on the particular question, we apply a reformulation to get a new task. We then resolve this new task, learning a lot about the initial plan and why we did what we did. Lastly, we use an LLM together with a question and both of these plans to write up a high-quality answer, which can then return to the human and explain why the system did what it did. This is where we stopped for the Beluga competition. And it's what was enough to win the competition. But it's not where we stopped with our research. We've continued in this vein of explainability and seized on a concept called facets. I won't get into what facets are because we don't have so much time, but I'll highlight 3 key points they do, which is really cool for us. First of all, is that they let us consider all plans in parallel. So previously we sampled one plan before and one plan after. Now we can look at all the plans all the time. Secondly, it gives us really fine-grained control. We can consider individual actions, and we can even see what a choice right now will make for our future choices later. Lastly, this comes in an interactive, near real-time system at the moment, so it's actually human compatible and so on. But those of you who are very peculiar eyes, you can probably see this as a demo up there. So that's where we have Daniel right here, ready to show us this facet reasoning system live, currently called Plan Pilot. So thank you, Daniel.
Thank you very much. Yeah, so basically, since finishing, or like since submitting our final version for the competition, we've kept working on a system that we call Plan Pilot, because it kind of allows you to navigate the space of plans of a given planning problem. And I prepared a video on that, and I might need a bit of support from Florent. All right. Yeah, the system also comes with a web interface. First of all, we select our input PDDL problem. We compute an initial solution, pretty much the same as we did before. We set some parameters, and then we basically let the planner compute that solution. I chose a very short and small problem just to make it accessible. So what we see is the pre-selection in kind of purple, and then you can basically interactively say, well, at this particular point, I don't want to have a certain action. And then, well, in the back, we do some reasoning, and we see, well, if an action turns gray, it means although it's not preset by the planner, we still have no choice, so we have to take that action. And once we, what I'm doing here is basically deactivating some of the planner choices, and then later on activating some others, like actions that the operator might want to have at a certain point. What we see on the right is the input plan, basically all the time, and then at some point we could be kind of just happy with what we got, interactively exploring all the possibilities, and the options that we see here is basically always something that will lead to a proper plan. So it's not that you can select something that doesn't turn into a plan. This is a second view. So maybe let me get back for a second. Yeah, so essentially it is like an interactive way. You start from a seed plan that is given by, for us, it's fast downward, but it could be coming from the Hive. We don't really care. It has to be a sequential solution, and we take that as input, and in the back we do some reasoning about alternatives, like what if we disallow certain actions, or we want alternatives to happen at certain points along the plan. All right, the second view is something where you go the other way. So you don't start with an input plan, but you start from scratch. So here we don't pre-select any action. We fix some parameters. And then what we list what we call these facets, which are essentially choice points along every solution. So all of the facets that are listed here is something that you could do. So if, for example, you could deliver to hunger in time step 6, and we can activate or like enforce or forbid these kinds of actions. We can kind of filter by action type. We can filter by time step, so we want to display only the options that we have at time step 2. Then we kind of force that action to happen in this point, and then we deselect the time step, because then we see the options for the remaining time steps. So overall, it's a very interactive way, so you get to see all the options that you have for solving that particular planning problem, and you kind of navigate the space of solutions by selecting preferences in terms of some actions that you definitely want to happen at a certain point, or some that you want to forbid to happen at certain points. And you can also kind of abstract away from the time points. You can just say, well, I forbid a certain action to happen ever along a plan, or I want some action to happen somewhere along a plan. Then a bit more statistics. What we can do is counting the number of facets. That's important when you're talking about robustness. So if you did some selection and there's only very few facets left, so very few choice points, that means that you've restricted your solution space quite a bit. So there's not many solutions left that satisfy the constraints that you've provided, and that might indicate that you're not very able to account for uncertainty happening, like a change in the flight schedule, for example. So that's something that we can actually quantify. So for all of the facets, it's not so interesting for the ones that are that have been activated, but for those that are not activated, so for the ones in blue, that's something we selected, and here's something that we have not selected, and this measures will basically tell you if you activate that facet, then you're reducing the space of choice points by 34%, and you will have like 100 choice points left. So this is really like a way for the engineer who will be looking at this to understand, well, what implications do my changes have? Like if I enforce a certain action, what does that mean for the remaining solution space? How many solutions are left? And basically what other actions are implied. So this is basically what you see here. Given this choice of facets, so we've activated these 4 facets, forbidding the first 2, enforcing the third one, and again forbidding the fourth action to happen at that time step. You can at every point in time list the implied actions. So this is basically, given this choice, those actions here will have to be taken at these respective time steps. So basically, iteratively, you can kind of converge towards solutions that you might prefer more than others for reasons that are usually not being accounted for by automated planners. All right, so once you've navigated your solution space and you're kind of happy with what you see here, you can also let the tool just output a solution. You can output one, you can output all of them. Usually that's like really thousands or millions of solutions, even for such very small problems. And then you can basically get your solution, take another look, and then go back to the navigation, or just be happy and fix that plan for your current instance. Yeah, that's basically all about my demo. I very much liked to work on this because it's a very unusual way of solving planning problems. Usually we just feed our problem to the planner, we get something out, and if you don't like the solution, you need to modify the PDDL, you need to change something in the algorithm to get the different solution. And here you have a very systematic way of exploring the solution space of planning problems. All right, I think that's mostly it. Yeah, that's all. Thanks. All right, so this is all about our demo, and I'd like to again say thanks to the organizers, thanks to the Machine Reasoning Lab in Linköping University. If you want to find out more about our lab, here's a QR code, and we've also just gotten accepted a workshop paper at the ICAP's HaxP workshop that is basically describing the demo that I just showed you in more detail and our approach to what we basically did in the Beluga challenge. So with that, I'm also happy to take questions, of course. Thanks.
Thank you very much for this great team talk. Are there any questions? And here, yeah,
so Elliot said, and it was on your slides, so you can explore all plans in parallel. So what's under the hood? And okay, what size problems we're talking about?
Yeah, sure. I mean, scalability is for sure not easy. So right now we're working with an answer set programming encoding of planning, where we just use like a plain translation from PDDL to ASP. And then there's existing tools that allow for facet navigation. So we're basically building on one of these tools we are working on the ASP of the planning model, where we already do some kind of pruning, like pretty standard techniques that are, for example, used in fast download to shrink the size of the problem. So what we can support is some of the like from the explainability benchmark set. I'm not sure how familiar you are with those, but basically half of the benchmarks we can handle kind of efficiently within the time scope of the competition, so within the 10 minutes. This what I showed first, where you start with a seed plan. So essentially that makes the reasoning much easier because you are searching a much smaller space. So if you start with that, then making modifications is much more efficient than starting from zero and just really exploring all plans in parallel.
Okay, thanks.
Any questions remotely? No? Okay, I maybe have one last question and then we can ask you more questions during the cocktail. So I was wondering how much depends on the PDDL encoding and whether it can be generalized to other planning problems, in fact.
That's a good question, yes. So what we're using in the translation from PDDL to ASP is like a very, very basic variant. I would say that ASP might not actually be the method of choice. So there's also this facet reasoning exists for SAT-based solutions as well. And then I would say everything that you can reasonably encode into SAT is something that you can use for this facet reasoning and this kind of solution-based navigation. So if you're willing to encode your problem into SAT, then I think you have like a lot of freedom, and the tooling is actually not is quite advanced. I would say like this facet reasoning is something that has been introduced in the ASP community only a few years ago, like 17, 18 around that time. But the tooling is pretty robust. So they're basically building on top of existing ASP technology, the solvers, and same for the SAT. So I would say that there's of course this modeling issue, but if you have something or if you can encode your problem in PDDL, then having like a more direct translation to SAT or ASP is probably very manageable.
Okay, great. So I guess we can get more information about facets in the cocktail. So that's the end of the official presentations for the ceremony. So we can say, so thanks a lot again. So that's then the end of the presentation now. So bye-bye people remotely. And for the one who have the chance to be here, we now have a cocktail just outside the room.
Thanks a lot. Very interesting. Congratulations to the winners and enjoy the cocktail.
Uh,